Hello, in this video we'll be talking about finding the sample size for a t-interval. Okay, so a confidence interval using the t-distribution. So let's review real quickly. From an earlier video we talked about determining the sample size for a z-interval. So recall that when we have a z-interval we can first determine the sample size needed for predetermined values for the level of confidence, 1 minus alpha, and the margin of error e using this formula. Take the inverse norm of 1 minus alpha over 2, multiply by the known population standard deviation, sigma of the x's, or just sigma, divide that by the margin of error that we want to use, e, then square the whole thing, and then that gives you a, well, it may not be a whole number, but round up, always rounding up, to a whole number n, and as long as you have that n or higher, you will have at least the level of confidence and the margin of error that you need. In other words, you'll have that margin of error or smaller, or that level of confidence or higher as you build your confidence interval. Now, this is very important if you're working through this ahead of time, because you don't want to go out and necessarily spend a lot of time taking a sample all of a sudden to find out that your sample that you were taking was too small for the methods that you wanted to have occur. So you sort of predetermine a level of alpha, or 1 minus alpha, that you want, and then you predetermine a level of e and solve this. Now, of course, this works for a z-interval, but as we know, oftentimes we don't know the population standard deviation sigma. So what do we do for a t-interval? Well, the formula basically becomes this. When we do a t-interval, notice that we just replace sigma by s. We replace the inverse normal by the inverse t of 1 minus alpha over 2. And remember, our degrees of freedom is n minus 1. And this formula will find the same thing. Unfortunately, there's a problem here. And the problem is, well, there's a couple of problems. The first one is that we kind of need to know the sample size on both sides. Whereas this last formula, when we look back at it, the right side has no n's involved anywhere. The sample size is not related on the right side, so it's not needed to figure out the right side, so we can use this to solve for n. But that's problematic here because we can't do the inverse t if we don't know the degrees of freedom, which requires us to know the sample size. So this is not really truly solved for n. So that's a little bit of a problem. And the other problem is we need to have taken a sample or some other way be able to tell what s is ahead of time. And so both of those things are problematic here. And so we're going to sort of show you a workaround in this particular video that usually will get you pretty close to what you need for this result. But it is a bit of a workaround, these particular problems. So let's go ahead and take a look and see how we can address this. So just as in determining a sample size for a z-interval, what we need to do is get a maximum acceptable margin of error. So we don't want the margin of error to exceed a certain amount, and we sort of lock that in, an e-value. And then we also decide we want a confidence level, 1 minus alpha, and we lock that in. So let's say, for example, just so we have an example to work with, suppose we decide up front that we want our margin of error to be within 15 units, and we want our confidence level to be a 90% confidence level. Now, if you remember in the formula, it didn't use alpha or 1 minus alpha. What it rather uses is 1 minus alpha over 2. And as we've seen several times, the easiest way to get from a confidence level to a 1 minus alpha level is to just add 1 to the confidence level and divide by 2. So instead of 0.9, make it 1.9 and then divide by 2, and you get 0.95. So if 1 minus alpha is 90%, 1 minus alpha over 2 is 95%. We've seen that several times. Now, so we have that set up. This is so far just like we would do if we were doing a z-interval. Now, what we're going to do in this particular method that I'm going to show you here is we're going to pretend that we're finding the sample size for a z-interval, use that as the first estimate for n, then using that value for n, we'll use that in the formula for the t-interval to get our final estimate for n, which will be just a little bit bigger than what it would have been for the z estimate. So let's take a look at how this will play out. Now, we also have another problem is we need to somehow have a way to estimate the standard deviation. Now, there are a couple ways we could do this. One way we might do is we might do a pilot sample and use the sample standard deviation from the pilot sample to approximate the population standard deviation. Or we might have some sort of historical data indicating at least an estimate of the standard deviation. And either way, we use this in place of sigma in the formula for the sample size for a z-interval. And if when in doubt, you need to overestimate sigma at this point. Okay, so if you're not sure about the sigma, overestimate it or round it up to get some kind of estimate for sigma. So let's, or sigma or s, either way. And let's call that 25. Let's say we've done that. For some way or another, we've come up with an estimate of s or sigma is 25. Now, we use this information in the formula for the sample size of a z-interval and just going to round it off, not round up or down, but just round off to the nearest whole number and let this be our first estimate for n. We'll call that value n1. So in this case, our formula, remember, is inverse norm of 1 minus alpha over 2 times sigma of x's divided by e, and then square it. Now, we don't know sigma. If we did, we would be doing the z-interval, and that would be it. But we have some estimate, and maybe that's from a pilot sample. And we put that in as 25. Our margin of error we're willing to work with is 15, and our 1 minus alpha over 2 level is 0.95, and then square that. So you can see it typed in a calculator. Parentheses, inverse norm, 0.9501, close parentheses, times 25 divided by 15, close parentheses, square it. 7.5 something, that's 5 is bigger than a half, or the second digit is 5 or bigger, so we go round up to 8. And so there's n1, and we'll use that as our first rough estimate. So it's looking like a sample size of around 8 is probably going to do, but it's probably going to need to be maybe just a few bigger. And so we're going to take that value in hand and go from there to adjust it for a t-interval. And the way we do that is now, let's see what we have so far. We have our error, margin of error is 15, our 1 minus alpha level is 0.95. The s we're assuming is 25, and n1 is 8. Now, if that's the case, we can go back to our formula like this, use n1 minus 1 for your degrees of freedom, and that should say 7 there, not 6. Let me fix that. Okay, that's fixed, and I think the rest of it's correct. So if you look at this, so that's inverse t of 1 minus alpha over 2, n1 minus 1 times the s over e, take that and square it, and then round up. This time you round up no matter what. So if it would have been 9.1, we'd still round off to 10, round up to 10. So anyway, you can see how I typed it in the calculator right there, and I got 9.97. Round up to 10, and so 10 should work as long as the s, well, a couple things we need, I'll go over that here in a minute, but as long as the s is not bigger than 25, and as long as we can assume that a t-interval is appropriate, that is the distribution of sample means is approximately normal, we see that a sample size of 10 should work. So that's kind of our estimate, that's our method for finding a t-interval sample size. So let's review real fast. So we want to use this formula. We can't really do it straight out, so what we do is we use this formula for a z-interval. So we decide on some confidence level and error that we're willing to do. Use the formula here for n for an e, round it off to 8. Then once you have that in mind, then we go back to this formula right here, which is the t version, plug in the 8 here for n1, which makes this 7 degrees of freedom, and plug in the rest of the information there using our estimate of s as well, and then round that up to a whole number, whichever one comes next, and that's our estimate. So that's how we do it. Now let me just point out that we want n to be, this is the formula that we have, we want n to be greater than, or at least greater than or equal to, inverse t of 0.95, n minus 1. Remember the s was 25, and then 15 here for E, and squared here. So we're assuming we know the S that we're wanting, which is a sample standard deviation. Okay, and as long as if we assume that, then we want the right side to be less than the N value. So I can sort of check out to show you that the 10 that we produced was a correct value, at least in this case, because I can put the right side in as a formula with an X in place of N. And then if I make a table for it, which is what I've done here, so I put this in right here in my calculator, say this is a TI-84 calculator, press Y equals, put in the formula here, and I just started a table at 8 going out by 1s automatically. So this X value is the N value, the left side, and the right side is the Y1, and we want to find the first X that comes out, which is bigger, where X is bigger than Y. And if you look, 10 is the first time. 10 is the first time that does happen. So 10 was the appropriate thing to produce there. Okay, and then to finish up, let's notice a couple of things. So the sample size generated by this technique here should produce a confidence interval, a T interval, with the desired level of confidence and margin of error, or better, if the following two conditions, both of them, are met. First of all, the distribution of sample means must be approximated well by normal distribution. So remember, that works fine if the original data, if you're pretty convinced that it's pretty much normal or close to it, very close to it. This will work even with the lower sample size, like say the 10 that we just determined in our example. The other thing that we need is the sample standard deviation in our sample does not need to exceed the estimate we used for S in our computations. Either one of these could slightly throw things off, or the further off they are, the further things could be off. So remember that if we know the distribution of individual values is close to normal, then a relatively small sample size, like the 10 produced by this method in this example, would still be okay. And so you can get by probably with the sample size of 10. However, if you're not sure ahead of time that the distribution of individuals is nearly normal, then remember you need your sample size to be at least 31, bigger than 30, to satisfy the normality constraint. So in practice, if it's not too problematic to get a sample size in the 30s, then at least use a sample size of 31, and if this method produces a larger number, then go with the larger one. But if it produces something smaller than 31, go with at least 31 or bigger. The other problem is if the sample size turns out to have a higher standard deviation than our estimate, our sample size could be a bit low. So when you're working with the S in the calculation, then a couple of things you could do is, number one, you want to perhaps even overestimate S, or you could even add a few to the sample size when you get your final answer. So that would give you a safer value for N. The other problem, of course, is you do have to estimate S somehow before you do this, which means maybe you have to actually take a sample. So what you might try to do is you might try, if you have no idea what S is, of course you could just try to take a sample of size 31 or something a little bit bigger than that, and just see if it gave you the level of confidence and margin of error that you wanted. If so, you're done. If not, and you need a quite a bit bigger sample, then this method will tell you how big you need to take your next sample to make sure that it's going to be the size that you need. However, of course, if you have some historical information about S, then this will give you some kind of way to go at this that'll make it a little bit better. Okay. Finally, I just want to say, in my particular class, my probability statistics classes, the only time we're going to use this particular method will be on one tutorial question on the homework set, and it will kind of step you through this process that we just did here. But I will not ask a question over this particular topic of finding a sample size for a T-interval on the practice test or the exam. So if you can just get through that one tutorial question and get an idea for this, it won't be on the test. However, this is kind of an important idea because T-intervals are definitely more realistic and much more used in practice than z-intervals, and it is useful for us sometimes to know how to turn this around and find the sample size up front, hopefully, or at least after a pilot sample to see if we've got a big enough one if our sample is not as big as we would like.